Hi everyone, and welcome to today's webinar brought to you by Exida. This afternoon we're going to go through predicting proof test coverage with an FMEDA. My name is Paddy Healy, and thank you everyone for joining in with us wherever you are. Hopefully you have a nice cup of coffee in hand to get ready for this. So yeah, as I say, we're going to go through predicting proof test coverage with an FMEDA. We're also going to use the kind of spreadsheet example, so there's a practical element to this as well, not just the kind of theory behind proof test coverage. And really, proof test coverage, it's a measure of how many undetected dangerous failures are detected by a proof test that you may implement in your particular product or your design. And obviously in functional safety, one critical performance metric is called the PFDavg, and this is the average probability that a safety protection function will not work when it's needed, and this is calculated. So again, just to remind everyone, this is the fourth in a series of 8 webinars that Exida are running over these coming weeks. Tomorrow we have another one again. Just if anyone hasn't signed up already and is interested, it's on the component data requirements for an FMEDA. So that one's tomorrow. They're all free, so if you get an opportunity, sign up and tune in. So yeah, just a bit about Exida. Company was founded over 23 years ago by several of the world's top reliability and safety experts. And as you can see, the company's just grown over those 23 years. It's now a truly global company. And yeah, professionals around the world, they definitely come to us when they're looking for expert guidance when it comes to functional safety. Some of the offerings from Exida, we just kind of 3 facets to the company. We have the engineering tools division, we have the certification and assessment, which I am part of. So my day job is kind of doing FMEAs, FMEDAs, and doing certifications on products. And then we have the system lifecycle services division. Now, an interesting part of the engineering tools division is a software development team, and many of the tools that people out there use, and obviously we use internally, are developed in-house by Exida and the engineering tools division. So we'll talk a bit more about them as these webinars go on. So a market report back from 2015 showed that Exida was the global leader in safety device certifications, and specifically in the logic solver category, where certifications were done over 40 years ago now. Exida has now overcome that 20-year head start to become the leader in that particular logic solver category. So just before we get into the proof test coverage, just to recap a bit on FMEDA in general. Obviously, a good FMEDA starts with a good FMEA, and to do an FMEA, you start looking at your architecture, your system level design. You break it down into the sub-blocks of that particular design. Some of those sub-blocks may have a further breakdown into more sub-blocks. So for example, a power supply may be further broken down into logic level power, high voltage, isolated voltage, whatever it happens to be. But for each of those sub-blocks, you then describe the failure mode and the effect of those failure modes for each of those blocks. That then allows you, when you get to the component level, to start mapping the failure of each particular component in a block to the failure of that particular block that it's housed in. So again, using the power supply as an example, we were looking at a regulator IC component here. We're doing the analysis. We get the failure modes. These failure modes come from our component reliability database, and then the failure rates are also they come from our particular database. And you do this for each particular component in your particular design. So an FMEDA is a quantitative approach. So the outputs from the FMEDA, as they're listed here, but the main one that we're going to look at this afternoon is the coverage factors for each defined proof test. And these are very, very important, which we'll explain as we move on. But firstly, we'll just look what is a proof test, and we're going to look at a couple of examples to kind of help us explain that. So in an operating process, often the process is shut down to a condition where the hazards or the dangerous conditions cannot occur. Therefore, the automatic protection system is no longer needed. In the shutdown state, it may be possible to run tests to detect potentially hidden failures that are not practical when the process is running with hazards present. So for the first example, we have an autonomous cleaning robot. It returns to the charging station once a day. And a particular proof test that might be applicable in this situation is when it returns to its charging station, the brakes could be tested. Obviously, you can't really check the brakes when it's in full operation mode, when it's been used during the day. So the automatic diagnostics may not detect failures with the brake system, but they can be done as a proof test when the system is in a more shutdown mode. Another example here, in a chemical plant, a process unit is shut down every 2 years into a safe state. The safety function equipment can be tested using the defined proof test procedures. So here we have a list of the kind of proof test procedures. The first one, a pressure sensor is connected to a manifold where the input pressure is isolated and a test pressure can be applied. 4-point test is done. The output is measured. If the output does not indicate that the test input within specified accuracy, the test has failed and revealed a potentially dangerous failure. The device requires replacement before further operation. Another proof test is a 4 to 20 milliamp current generator is connected to each analog input. The logic solver is checked to verify the generator signal, and the logic solver internal variables are the same within the specified safety limits for a 4-point test, and so on. So proof tests are generally things that are not generally, proof tests should be a test that is done to detect failures that the automatic diagnostics do not detect. So what is the proof test coverage? In an FMEDA, the proof test coverage can be accurately predicted. In a conventional component level FMEDA, the proof test coverage can be an estimate for each component failure and entered into a spreadsheet. In the FMEDA, or in our case, we use the FMEDAX tool, proof test coverage is estimated for each architecture block deviation. This approach is much less time consuming. But the main thing to take from this particular slide is that not all dangerous failures are detected. Which dangerous component failures does the proof test detect? Which dangerous component failures are not detected? And how many of those component failures are already detected by the automatic diagnostics? So maybe another way to describe the proof test is a strategic proof test. And many proof tests were created when automatic diagnostics did not exist. Relay logic from the 1970s, 80s, but things are very different now. So we're going to create a new definition. A strategic proof test is a test done to detect any failures not detected by automatic online diagnostics. And with a strategic proof test, we can design proof test procedures that are easier to perform, cost less, and are more likely to get done. By understanding the actual dangerous undetected and the enunciated undetected failures in our instruments, we can significantly improve our test coverage as well as lower the cost. And finally, we can detect program changes via tools built into most products. So if we come back to our second example we looked at there, and this one was where we applied a 4 to 20 milliamp current into our particular device. However, this architecture, when we looked at it closely, this particular architecture has good analog inputs and excellent diagnostic coverage. The proof test detects nothing that hasn't already been detected by the automatic diagnostics. So therefore, this would be given a proof test coverage of 0%. And basically, this test should certainly be eliminated from the proof test plan, as it does nothing. So getting into a bit of the theory behind proof test coverage and the probability of failure on demand. The PFD is a measure of the likelihood of a system failing when it is demanded to perform its safety function. If a perfect proof test is performed on the system and any failure is detected and repaired, then the PFD should decrease. The reason for this is that the proof test will have identified and corrected any potential failures in the system, therefore making it less likely to fail when demanded to perform its safety function. So I suppose the next question to ask is, so can we conduct a perfect proof test? So in a perfect world, we would conduct a proof test where every single undetected failure would be revealed and the device would be restored to an as-new condition. Unfortunately, in the real world, this rarely happens. The reasons for this could be that the proof test may not be carried out under the exact process conditions. For example, a device may be taken away from its normal operating environment, temperature, humidity, various different things, and brought to a bench, and the proof test may be carried out there. So they are not the exact same conditions as to where the device normally operates. Also, there is difficulty in testing. An example could be ensuring that a valve is gas tight after operation, or obviously ensuring that your reference meter or your equipment that you're using to do the test is calibrated correctly. So at the start of the probability of failure of the safety function, as we can see here, at the very start, at this particular point, the probability of failure is low. But obviously over the mission time or a particular time interval, if a hazard occurs at this moment, the probability of a SIF failure has obviously increased if the demand is high. So I suppose the next question to ask is, what value of PFD do we use when we're doing our calculations? When we're looking at that particular graph, what we need to note is if the events, and this helps us in trying to streamline down the formula that we're going to use when doing our PFD calculation. If the events that cause a demand are independent from failures in the SIF equipment, then an average value is appropriate. So from that assumption, we can now, and this needs to be clarified, that this formula here, the PFD average, which is approximate to the dangerous undetected failures multiplied by the time interval divided by 2, this particular formula is for a perfect proof test, which, as we have already described, does not exist. So what happens to a PFD when you have an imperfect proof test? Or another way to put it, what happens in a real proof test? It can be clearly shown through detailed analysis of devices and examples that no real proof test is perfect. There are many examples of failures in products that cannot be detected by proof testing. An obvious example of a proof test done by putting a blocking device on an actuator, as we have here, and checking to see if the actuator valve assembly attempts to move. This does show that a portion of the subsystem is working, but the test gives no indication of the health of many parts, including the valve seat. Did the valve actually seal? This test cannot tell. So back to our graph and our formulas. At the end of the proof test, it is known that the probability of failure is reduced, but it's never reduced to 0 because not all failures are detected. The probability of failure is reduced to some value above 0. Obviously, the probability of failure will increase after each proof test. So for the first one, we have our time interval, and as the curve rises, obviously as time goes by, the probability of a failure increases until we have that failure, and then obviously we intervene and the system is reset. But that, as we said, it's never reset. The probability of failure is never reduced to exactly 0. This continues for the entire mission time of the system. And what you will find is that over time, the impact of an imperfect proof testing will result in a gradual increase of your PFD, which may eventually lead to your system not meeting the PFD requirement and reaching an unacceptable level. The effect of an overhaul will restore the device to as-new condition and will reset the PFD to its original value. Therefore, the probability of failure on demand as a function of time for an imperfect proof test is a rising sawtooth waveform, or should I say, instead of an imperfect proof test, is a more realistic proof test. So the formula, if we look at it here, and again, just to mention to everyone, you will get a copy of these slides. I'll give you the email address to contact after the webinar to reach out to get them. But anyway, the probability of failure on demand, the PFD average, can be approximated to the proof test coverage multiplied by the dangerous undetected failures multiplied by the time interval divided by 2. But what you also need then to add in is the proof test coverage that doesn't detect any dangerous undetected failures times the dangerous undetected failures over the entire mission time divided by 2. So we'll look at a more practical example by actually plugging in some figures to see what we get. So again, the formula just rewritten here from the previous slide. We have our failures detected by the proof test, and we're going to condense that down to DDPT, that's dangerous detected after proof test. And then failures not detected by the proof test will be dangerous undetected PT after proof test. So the PTC, the proof test coverage, can be calculated when we know the number of dangerous undetected failures before and after the proof test. So there's our formula, and we're going to use an example of dangerous undetected failures of 100 fits. For a defined proof test, we estimate the proof test coverage impact for each component failure mode. The FMEDA results show that a dangerous undetected after proof test of 20 fits. So again, as I say, everyone will get these slides afterwards, and so you'll be able to kind of spend a bit of time and work through all the different examples in the slides. So back to our spreadsheet that we looked at last week, and what we've done here is we've added in a column for our proof test coverage. And what we need to do now is scan down through our slides and look for any of our components that were not captured by the diagnostic coverage. So first off, we define our proof test, and this is up to you as the system designer. You know your design, you know your components, so you're able to describe the proof test that will most capture anything that's not normally detected by the automatic diagnostics. So as I say, we've scanned down through our spreadsheet looking for all the dangerous undetected failures, and 3 that in particular that jump out at us is the flasher input dangerous undetected failures of 6.9 fits. The LED flasher control is a dangerous undetected failures of 15.86 fits, and then the LED array is a dangerous undetected failures of 150, rounded up 153 fits. Now it needs to be stated again that these are failures that were not detected by the automatic diagnostics. So we are going to now have to try and describe a proof test that will capture or test these particular components in an offline state. So here's an example proof test. We disconnect the flasher input from the signal source. We connect an open switch between the 24-volt power terminal and the flasher switch input. We close the switch and observe that the flasher will flash at a 50-50 duty cycle once every second. And while the light is on, we try to measure the light output and make sure that it's at 500 lumens or more. Remove the switch and reconnect the flasher input to the signal source. This is a full functional test. It flashed when required. How could this test be anything but 100% proof test, have anything more than 100% proof test coverage? And I suppose the thing we need to, we're taking these figures, these estimates, they're based off IEC 61508 of high, medium and low and none. And obviously the reason we don't go up to 100% is number one, the figures are conservative, but we have to allow for the human factor. In an automatic diagnostics, obviously the system is running, it's doing its diagnostic, but with a proof test, you have that human element where the operator intervenes to run a test. So because of that, we will not give it 100% proof test coverage. But as I say, these figures here from 61508 are conservative. They could be somewhat closer to reality, but that would require thousands of tests to get a statistically relevant result. This would take up far too much time. And after all, you know your design, as I said, and your circuit. So based on the definitions above, you can use one of these percentages that most closely matches your proof test. So obviously for a high proof test, a component or failure mode will be detected by a simple, easy understood proof test that is part of the defined proof test procedure. So back to our spreadsheet. Again, we scan down through our spreadsheet, and if we look up at the very top there, we have our optocoupler. And as you can see, we have two particular failure modes that had an undetected by the automatic diagnostics. So that's down there. And as you can see here, we're just double checking under the DC, the diagnostic coverage, you can see that it's 0%. So yes, definitely these two failure modes were not detected by the automatic diagnostics. We've defined our proof test, and we are sure that our particular proof test will have a 99% coverage. So what we do then is enter in the proof test coverage into the particular column for each of our particular components. So the LED flasher control initially had a DU of 15.86, and after our proof test, this has dropped down now to 0.16 fits. So it's a very successful proof test. So we're looking now at our LED array. This initially had a dangerous undetected failure of 153 fits, and after our proof test coverage, this has dropped down to 15.81 fits. So again, a very comprehensive proof test. And looking at the entire system, we had a total dangerous undetected failures of 175 fits. These are all the failures not detected by automatic diagnostics. But after our proof test, this failure has dropped. These failure rates have now dropped to 16 fits. So again, a very successful proof test. So just looking at the calculation, our total DU was 175. After a proof test, it was 16. So using the formula DU minus DUPT, dangerous undetected minus the dangerous undetected after our proof test, this gives us a dangerous detected after proof test of 159 fits. So plugging this into the formulas that we looked at previously, this gives us a proof test coverage of almost 91%. So again, as I say, a very good proof test. And the key element, as I said, when you're doing your proof test is to ensure that any of the tests that you do in your proof test haven't already been captured by the automatic diagnostics. And that's why it's key to describe and do your proof test while you're doing your FMEDA and analyzing your particular circuit. So as we've said previously, whether you're using a spreadsheet or an FMEDA tool, it makes absolutely no difference. You can get the same results, the same outputs. It just, some require a bit more work than others. But there are some of the key features to look for if you're looking to get an FMEDA tool. Again, the one that we use at exida here is the OMX suite, and that allows us to go all the way through from our requirements, our system architecture, and then through into our FMEDA. And the core element of the tool is the component reliability database. So in conclusion, safety can be significantly improved with a proof test. Although traditional FMEDA is not considered has not considered proof test coverage, a prediction can be made while focused on each component. And that's what I was saying. While you're analyzing each component and doing the FMEDA, you can then do a further analysis to see if this particular component's failure is not detected by the automatic diagnostics, describe a proof test that will detect failures. Proof tests should be designed to detect failures, as I said, not detected by the automatic diagnostics. Proof tests should be made as simple as possible to avoid human errors. The trend is towards semi-automatic testing. So just to remind everyone, these are the webinars we have coming up. Obviously, we're 4 in, we've another 4 to go over the next couple of weeks. So if you haven't already, please sign up. They're free. The links are on exida's website. So yeah, look, again, at this point, I just Really like to thank everybody for your time and attention today. It's been brilliant. Love doing these webinars. So check out the list, sign up, and hopefully see you over the next couple of weeks. Thank you.